Using truth tables to determine the validity or invalidity of arguments. So there are two methods that we can use when trying to determine the validity or invalidity of arguments using the truth table. We can either use the long truth table or we use the short truth table. Now, the difference between the long truth table and the short truth table is that the long truth table sometimes can become very cumbersome when you have so many variables in such a way that you may begin to have like 32 rows, 64 rows, and your notes or your text may not be sufficient, may not be enough to contain the values you want to present. But with the short truth table, no matter the number of variables you have, you'll be able to analyze that argument in just one line. So that's the difference between the long truth table and the short truth table. So generally, there are two definitions that will guide our activities here. The first definition is that if an argument is valid, then it will be impossible for all its premises to be true and its conclusion false. This definition of validity is very important. And the second definition of validity that will be guiding us is that if an argument is valid, then its corresponding conditional must be tautologous. In this case, you will need to convert your argument to a conditional statement. Let's begin with the long truth table. In using the long truth table, we can employ the two definitions I've just given of validity that have just been given. Let's begin with the first definition of validity, which says that if an argument is valid, then it will be impossible for all its premises, all its premises to be true and its conclusion false. What you do is that you plot a truth table for the arguments that you have been given, beginning with the premise or premises, if you have several premises there, and then ending with the conclusion. After doing that, you inspect your table. After plotting the truth table, you inspect the table under the major connective, because under the major connective for whatsoever values you have given, you inspect the table and you'll be looking for something. You'll be looking for any row where all the premises are true and the conclusion is false. If you find any row where all the premises, take note of that, all the premises, not just one premise is true, the other one is false. No. Once you find any row where all the premises are true and the conclusion is false, then that argument is invalid. But if you inspect the whole table and there is no row at all where all the premises are true and the conclusion is false, then the argument is valid. The point is that every row in an argument on the truth table represents a possible world. So if you discover any row where all the premises are true and the conclusion is false, then it means that there is a possible world where that argument is invalid. And for that reason, it is invalid. For an argument to be valid, it must be valid in all possible worlds. All possible worlds. Take a look at this example. We have premise 1, P conditional Q. Premise 2, Q conditional P. Conclusion, P wedge Q. What you do is to write your argument on a straight line. P conditional Q, P conditional Q. Q wedge P, Q wedge P. And then the conclusion is written last, P wedge Q. You plot a truth table for it. By now, we should know how to plot a truth table. You plot a truth table for it. There are two variables here, P and Q. So you are going to have 4 rows. 1, 2, 3, 4. There are 4 rows. So which means you have true, true, false, false. And then Q becomes true, false, true, false. This is Q, so Q must take the value of Q, which will have to see be true, false, true, false. And P will take the value of P, true, true, false, false. P must take the value of P, true, true, false, false. And then Q will take the value of Q, which is true, false, true, false. Having done that, you rely on your knowledge of logical connectives to give value to the connectives that you have there. Begin with this parenthesis. It's a conditional statement. Antecedent is true, consequent is true, it is therefore true. A conditional statement. Antecedent is true, consequent is false, it is false. A conditional statement with a false antecedent is true. A conditional statement with a false antecedent is true. You are done with this. So you can come to the next premise here. See, they are separated by a thick line. It's a conditional statement as well. Antecedent is true, consequent is true, it is true. A conditional statement with a false antecedent is true. Antecedent is true, consequent is false, it is false. A conditional statement with a false antecedent is true. So you have given values to this. You now move to the conclusion, which is a wedge, a disjunction. A disjunction is only false when both disjuncts are false. Otherwise, it is true. So you have true, true gives you true. True, false gives you true. False, true gives you true. False, false gives you false. Because it's a disjunction. It is only false when both disjuncts are false. So having done this, you have succeeded in plotting the truth table. So you inspect the table to see if there is any row where all the premises are true and the conclusion is false. This is the premise. It is true here, it is true here, and it's true here. So it passes here. It is false, it is true, it is true. It passes. True, false, true. It passes. True, true, false. It fails. Because there is a row 4. 1, 2, 3, 4. This is the fourth row. There is a row where the premise 1 is true, premise 2 is true, but the conclusion is false. So there's a row where all its premises are true and its conclusion is false. For this reason, this argument is invalid. So you just tell us, invalid, row 4, and tell us, if you don't want to say row 4, just come here and highlight where you have it, or you circle it as you want. And just ensure that you make your answer visible. So, the second example, P conditional Q, therefore negation Q conditional negation P. What do? There are two variables here, so you have 4 rows. You have 4 rows. True, true, false, false, true, false, true, false. Now, this is negation Q. Negation Q is false. How do you get negation Q is false? Because if Q is true, negation Q will be false. If Q is false, negation Q will be true. If Q is true, negation Q will be false. And if Q is false, negation Q will be true. The same thing with P. So for P, where you have true, true, false, false, negation P will be false, false, true, true. So you plot your table. It's a conditional statement. A conditional statement with a true antecedent and a true consequent is true. But true antecedent, false consequent is false. A conditional statement with a false antecedent is true. With a false antecedent is true. You move to the conclusion. A conditional statement with a false antecedent is true. A conditional statement with a false antecedent, with a true antecedent and a false conclusion is false. When the antecedent is true and the consequent is false, is false. And then with a false antecedent is true. With a true antecedent and a true consequent is true. Having plotted your table, you inspect to see if there is any row where all the premises are true and the conclusion is false. But since we have just one premise, you must inspect to see if there is any row where the premise is true and the conclusion is false. So it is true here, and it is true. The premise is true, conclusion is true. Premise is false, conclusion is false. It passes. Premise is true, conclusion is true. Premise is true, conclusion is true. So it passes. There's no row where the premise is true and the conclusion is false. For that reason, this argument is valid. So we move on to the second definition. Still looking at the long truth table. For the second definition now, what do? The definition says if an argument is valid, then its corresponding conditional must be tautologous. How do you go about this? You begin by converting the entire argument to a conditional statement in such a way that the entire premises becomes the antecedent while the conclusion becomes the consequent. And then you introduce the conditional sign to join the antecedent and the consequent. After doing that, you plot your truth table, right? And then you inspect your table under the horseshoe, which is a major connective that joins the antecedent and the consequent, which is the premise and the conclusion, to see if the values under it are all true, tautologous. When they are all true, it's tautologous, it is therefore valid. If it is not tautologous, whether it is contradictory or contingent, then it is invalid. Let's take a look at this. The same example we looked at while using the first definition. P conditional Q, Q conditional P, therefore P wedge Q. You convert it to a conditional statement. What do? You are to convert an argument to a conditional statement. What you do is that the premises form the antecedent, while the conclusion forms the consequent. But you must bring the premises together with a conjunction, a dot. You introduce a dot, which means you are going to have P conditional Q dot Q conditional P. Then you already have the premises forming the antecedent, while the conclusion becomes the consequent. Look at it here. P conditional Q, parenthesis open, open parenthesis closed, dot the next premise now, Q conditional P, parenthesis open, parenthesis closed, and then brackets closed, bracket open here. So everything becomes the whole premise here. The whole premises have now formed the antecedent. This is now the antecedent. And then you introduce the conditional sign before bringing the conclusion, P wedge Q, which is now the consequent. So you see, we now have antecedent and consequent. The whole argument has become one statement, one conditional statement. And that definition, the definition we're using says, if an argument is valid, then its corresponding conditional must be tautologous. This is now the corresponding conditional. This is the conditional that joins the premises and the conclusion. So if all the values under this conditional are true, tautologous, then it's valid. If they are not, then it's invalid. So you plot your table. Everything is now on the straight line. P conditional Q dot, that's premise 1 dot premise 2, conditional the conclusion, which is now the consequence. You plot your truth table. By now, we should be able to take it for granted that we know how to plot the truth table. So there's no point repeating all this again. So you can use your knowledge of logical connective to plot your table, and then you have the value for this parenthesis, the value for this parenthesis. After doing that, you can then combine the values for this parenthesis and the value for this parenthesis to get this dot, which is a conjunction. A conjunction is true where both conjunctions are true. So true, true gives you true. False, true gives you false. True, false gives you false. And true, true gives you true. You see that? And then you have the conditional sign. So in order to get this, you must combine the value of this, the whole of this bracket, which is this dot here. You combine this value and the value for the conclusion, which is this wedge, to get this. So you have antecedent is true, consequent is true, it is therefore true. A conditional statement of the first antecedent is true, conditional statement of the first antecedent is true, and then antecedent is true, consequent is false, it is false. When you inspect the table, you get to see that its corresponding conditional is not tautologous. Its corresponding conditional is not tautologous. For that reason, this argument is invalid. So you see that this argument is invalid. So that's the point here. And when an argument is valid, then its corresponding conditional must be tautologous. It is not tautologous here. So you take a look at the next example here. You have P conditional Q, therefore negation Q, conditional negation P. So you convert this entire argument to a conditional statement. There is just one premise. So all you need to do is to present that premise as the antecedent. So there is no, you don't have to join it with any conjunction because there is no other premise. So the premise becomes the antecedent, while the conclusion becomes the consequent. So with what you have here, You plot your truth table. After plotting your truth table, you take note of the corresponding conditional. This is it. So the antecedent is true, the consequent is true, it is true. A conditional statement with a false antecedent is true. And then you have the antecedent true, the consequent is true here, it is true. In the last row as well, antecedent is true, consequent is true, it is true. So when you inspect your table, you will see that its corresponding conditional is tautologous. For this reason, this argument is valid. If an argument is valid, then its corresponding conditional must be tautologous. So the same thing is what uh, is what happens with the short truth table. So we'll take a look at the short truth table shortly.